All right, section 3.2, the PowerPoint voiceover. Quadratic equations, functions, and zeros. Finding zeros, objectives, finding zeros of a quadratic function and solving quadratic equations by using the principle of zero products. Second way is using the principle of square roots. Third, completing the square. And the granddaddy of them all is solving it by the quadratic formula. Quadratic function f is a function that can be written as in form of f of x equal ax squared plus bx plus c, where a is not zero. If a is zero, then the square term goes away. You've got a linear equation. Remember, f of x and y are synonymous. A, b, and c are all real numbers. The zeros of a quadratic function are the solutions that are associated with it. These solutions are referred to sometimes as roots. Quadratic equations can have real number or imaginary solutions. Two good videos I'm not going to show, but you can watch them out of the PowerPoint. Imaginary numbers are real, and visualization, I can say it, I guess. What are the A's, B's, and C's? Provided all the terms are on the same side of the equation, your A is a coefficient of your square term, your B is a coefficient of your x term, and C is a constant. So right here, if I brought the 7 over as a negative, my A value would be understood to be 1, my B value would be 6, and then my C value would be negative 7. Here, my A value is 1, my B is 8, my C value is 25. Here, A is 3, B is 5, and C is minus 2. You get the idea. It's straightforward. Quadratic equations, you studied them in intermediate algebra. The principle of zero products. Super simple, but super powerful. Here's what he's saying. If the product of two numbers is zero, then either the first number, the A value, is zero, or the B, or perhaps they're both zero. Zero product property. If the product of two values, two numbers, is zero, one of them has got to be zero. Maybe they're both zero. That's the only way you're going to get a zero product if one of the factors is indeed zero. Square root. Remember now, we haven't talked about this, but when we physically take the square root of both sides of an equation, we need to consider the positive and the negative square root. Here, taking the square root of x squared gives me x, and I have to take the positive and the negative square root of k. All right, two possible solutions. When you have a square term, you get two answers. Solving this equation, 2x squared minus x equals 3. Bringing the 3 over to the left side as a negative, factoring it like we did back in intermediate algebra. And then we say to ourselves, if the product of this first binomial times the second equals 0, if the product of these two numbers or values equals 0, then either the first one, x plus 1 equals 0, or the second, 2x minus 3 equals 0. Solving the left side, x is negative 1. Solving the right side, adding 3 to both sides, and then dividing by 2, you get a second solution of 3 halves. Now, in algebra, in math in general, you can check these. All right, so we go back, and in place of x, we substitute negative 1. You see it in red here in place of x and in place of x. Solving the left side, 3 equals 3, true statement. That tells me that yes, negative 1 was a solution. And then checking the second solution in place of x, I'm going to substitute in 3 halves, square it, subtract it. And doing the mathematics on the left side, 6 over 2 works out to be 3. 3 equals 3. It's a true statement that ensures me that 3 halves is the second solution. Quadratic. Second degree equations will have two answers. Sometimes those two answers are identical. All right, you have two answers, but they're both the same value, and we call it a double root solution. We won't run into that situation in our course. Solutions negative 1 and positive 3 halves. Notice this guy here is a binomial, and the best way to solve this is to bring the constant over to the left side as a positive, divide both sides by 2, and then take the positive and negative square roots. Square root of x squared is x, plus or minus. Plus, that's understood, or minus the square root of 5. Two solutions, a second degree equation, two answers, plus or minus the square root of 5. And when I square either positive square root of 5 or negative square root of 5, when I square that, I simply get the number 5 back. 2 5s are 10. 10 minus itself is 0. 0 equals 0. Yes, I know I have my two solutions, and they're correct. What happens in mathematics, not every quadratic can be solved by factoring. All right. For instance, take something like this guy here. The factors of 25 are 5 and 5. They don't add up to 8. If you use a negative 5 and a negative 5, you'd get negative 10. That's not 8. The other set of factors that generate 25 are 1 and 25, both positive and negative. Well, 1 and 25 equals 26. That's not 8. Negative 1, negative 25 is. In other words, you can't factor this. So mathematicians were presented with this problem, going way back into the ancient Greeks. So they sat around trying to figure this out. And what happened is they came up with a way of figuring how to factor a quadratic, how to solve a quadratic that could not be factored the traditional way. It's called completing the square. And he runs through the steps here about isolating the terms on one side, dividing the coefficient of the square term if it's not 1. You complete the square by taking half of the middle term and squaring it, adding it to both sides, and then expressing what's left as the square of a binomial. All right, I'll walk you through this. In fact, this next example. All right, we look at this. We bring all the terms on the 3x over to the left. No matter how many times you try to factor this, factors of 1 are 1. 1 and 1 is not going to add up to 3. This cannot be factored in a traditional method. So he says, hey, mathematicians came up with this way of solving it by completing the square. So what do? They isolate the two terms that contain the variable on one side. They put this constant on the right side. They're going to take half of this middle term. Half of this middle term here. The middle term is a negative 3. Half of a negative 3 is a negative 3 halves. And when I square negative 3 halves, I get 9 4. I'm sorry, I square half of a negative 3 is a negative 3 halves. When I square negative 3 halves, I get 3 4 negative half of it is 3, half of a negative 3 half. Half of negative 3 is 3 halves. And when I square 3 halves, I get 9 fourths. All right. Half of negative 3 halves here. Squaring that. Half of negative 3 is negative 3 halves. Squaring 3 halves um, is 3 fourths. Negative 3 fourths. Squaring negative 3 fourths gives me 9 sixteenths. So what I want to do is I want to add 9 sixteenths to both sides. All right, half of negative 3 is negative 3 halves. Negative 3 halves squared is 9 sixteenths. He doesn't show you. I wish he did. Now, to solve for x, I'm going to take the square root of both sides, making sure I use plus or minus, and then adding 3 fourths to both sides. I end up with x equal to 3 fourths plus or minus my radical 17 over 4. Once again, I'm taking, well, I shouldn't say that. What happened here, let me just go back up here. What happened is he had a coefficient of 2. And in processes, I need to get rid of this 2 by dividing everything by 2. All right, now my middle term here is negative 3 halves. Half of a negative 3 halves is a negative 3 fourths. Squaring negative 3 fourths gives me 9 sixteenths. Yeah, that's what happened here. He cleared out the 2. He had to have this coefficient as 1. All right. Now, that got old. This idea of completing a square got really old, especially when the numbers are larger and, working with fractions. So someone had a bright idea back in the day. I don't know when it was. You know, could have been, the year 10,000, the year 1080. There's no record of who came up with it actually and what year it came up. What happened is mathematicians took a general quadratic in the form of ax squared plus bx plus c, and what they did is they completed the square. All right, they divided everything through by a. They took half of b over a, which is b over 2a. They squared it, b squared over 4a squared. They added that to both sides. They subtracted b over 2a, took the square root. What happened is taking a general quadratic and completing the square, they came up with a generalized formula that'll work with any quadratic. It's called a quadratic formula. There it is. Minus b plus or minus the square root of b squared minus 4ac over 2a. You studied this back in high school, and also if you took intermediate algebra here, whatever college, or if it's Massachusetts, you studied the quadratic formula. you know, it wasn't invented actually. It was discovered or proved. All right, and a quick search tells us the early Babylonians were the first to record this, and when they recorded it, who the heck knows? We've been around for a long time. All right, quadratic formula. It's accredited to the Babylonians. Check out this video how quadratics are in real life. Quadratic equations in real life. So there it is. All right, my quadratic formula. I've got a great video, and it talks about programming your calculator to actually calculate the answers to the roots solutions to a quadratic equation. Not bad. All right. If your solutions don't contain radicals, because when you do it in the calculator, it'll give you your answer as decimals. It won't give you a radical. Calculator can't give you a radical for an answer. So it may be worthwhile. But as a whole, you gotta know the formula, have it written down in your notes. I, I, programming it is not bad, but is it absolutely necessary? No, only because of the fact that if your solutions contain radicals, your calculator will give you decimals. Now you can play a game. You can look at the answers, change each one of the four answers into a decimal representation, and match it up to what your quadratic formula is giving you on your calculator. But it's time consuming. So all that being said is memorize the calculator. And when I do the homework voiceover, I do it all manually using the quadratic formula. All right, here's an example. First thing we do is bring the 7 over, put all the terms on the same side of the equation. There's your A, there's your B, there's your C. And substituting in the opposite of B. All right, the opposite of 2 is a minus 2, plus or minus my B value squared minus 4 times my A times my C divided by twice my A value. And then this becomes what square root of, what happens is right here he could have separated these two. I don't know why he added, but he's going to add it and then separate it over here. 88, can be expressed as radical 4. The square root of 4, um, square root of 4 times 22. And then separating radical 4 and radical 84, square root of 4 here becomes the whole number 2. Now, what you recognize here in the numerator, there's both these terms contain a factor of 2. So factoring that out and expressing 6 as 2 times 3, you're going to see that 2's are going to cancel out, leaving you negative 1 minus the square root of 22 over 3, or negative 1 plus. And a lot of times people will use just a plus or minus sign and just write it with one fraction instead of separating it. All right, negative 1 plus or minus the square root of 22 over 3. And then if he ever asks you for the decimal representation, which he won't, you're taking this and changing it to a decimal. Your calculator will do that very nicely for you, if that ever happens. I doubt it. Now, the number under the radical symbol, all right, the radicand, the value under the radical symbol, this guy right here, this b squared minus 4ac, has a special name. It's called the discriminant because it discriminates, which is not a good thing. But it discriminates in the sense that if that value under the radical is equal to 0, you're going to get one real solution in a quadratic equation. If it's bigger than 0, you're going to get two different real numbers. If that value under the radical symbol is negative, well, taking the square of a negative number is going to give you an imaginary complex number. All right, it's called the discriminant. We don't really, to see the quadratic formula supersedes completing the square. Why complete the square when we get the quadratic formula? But we do need to know how to complete the square because there's 4 examples at the end of the 3-2 worksheet where I asked you for the center and radius. In 2 of them, in order to get the center and radius, the h and the k and the r value, you've got to complete the square. And, I'll walk you through those. So I'll walk you through those.